right, so we're about to start. We are fortunate to have David Gamarnik from MIT talk to us today about the symmetric binary perceptron. David was scheduled to be here, but unfortunately he's sick. So we are very grateful that he agreed to give a Zoom talk. So this is a Zoom talk. If you have questions, raise your hand, and I will try to relay them to him. Okay? All right, let's have David speak.
Okay, should I start, I assume?
Yes, please.
Okay, well, big thanks to the organizers for the invitation. I wish I could be there in person and interact. That's the point of the conference. I personally resent Zoom talks, but now I'm in the position of doing that myself. I have COVID, so it wouldn't be a good idea to come. And I can't believe the COVID is still with us. Well, apparently it is. And additional thanks, big thanks and gratitude to organizers for making this Zoom deliverable in such a short notice. And it's a pleasure and honor to give this talk. It's a joint work with Aaron Kieseldak, Will Perkins, and Changjik Su, and it's about Perceptron. A little bit of a history. Perceptron model dates back to actually 1943, and it about 15 years predates the official introduction of machine learning, so to speak. So the term machine learning was coined in around 1958, around the time when Frank Rosenblatt used a version of the perceptron in his image recognition implementation. But the perceptron itself was introduced about 15 years earlier. So it's a very old model. The version of the perceptron that you probably all of you are familiar is something like this. So you have a bunch of labeled data. So here the label is just two labels, color, blue and red. And you need to separate them into two clusters, two groups by a linear separator, which goes something like this. That's the most familiar, most well-known, much studied perceptron model, but that's not the version, that's not the perceptron model that I'm going to consider. Instead, our model looks something like this. Suppose you have a bunch of data in n-dimensional Euclidean space, and your goal is to find a vector which is as orthogonal to all of these vectors as possible, if that's possible. So here you're trying to find a quote-unquote classifier sigma, and this vector needs to be orthogonal to the data, and kappa denotes the margin of error. So it's not going to be perfectly orthogonal, but it needs to be somewhat orthogonal. And kappa signifies the amount of error that we are willing to tolerate. This version of the perceptron is also quite familiar and studied widely, and it actually appears in the context of the so-called memory storage. But I don't really know much of a background on what this means and what it has to do with memory and so on. So please don't ask me that. But nevertheless, this is a very interesting model from the probabilistic and algorithmic point of view. Let me now introduce the model somewhat more formally. So we fixed a subset here, and this subset is really, in our context, it's going to be an interval. And we have a bunch of data, m data in n-dimensional Euclidean space. Our goal is to find a classifier, this vector, from the set of allowed classifiers, sigma, capital sigma, such that every inner product of this classifier with the data lies in the set K. So for example, and that's the example that we will consider throughout this talk, suppose the set of classifiers is all binary vectors with n entries, n-dimensional binary vectors, plus minus 1. And the subset is just an interval minus kappa to kappa. So that I'm just formalizing this previous picture where every inner product needs to be in the interval, it has to have an absolute value at most kappa. Okay, so that's the model, and that's the version we will consider. But more than that, we will consider a random instance of this symmetric binary. So it's binary because it's plus minus 1 entries, symmetric because it's minus kappa to kappa, interval is symmetric. We will consider a random symmetric binary perceptron model. So this model is the one where these vectors, the data is generated randomly according to rather straightforward mechanism. So we have m data points. Think of those as rows in the matrix A. So A is the matrix m by n. Rows, m rows of this matrix are the data points. We will assume that those are generated IID according to the standard, according to the normal distribution with variance 1 over n. Variance is 1 over n is the convenient scaling choice. There's nothing magical about that. It just helps simplifies things a bit. So we have this random matrix A. We have parameter kappa. And what is our goal? According to the previous model, we want to find a binary vector sigma such that when you hit this matrix A with the vector sigma, well, you matrix by a vector, you get a vector. What we want is that every entry of this vector needs to lie in the interval minus kappa to kappa. And if that such a thing exists, we say that the binary symmetric perceptron model admits the solution. If not, we say that it does not admit a solution. Okay, so that's the model. And now a couple of questions, and then I will pause to see if you have, folks, any questions. First, we will consider this in the so-called proportional regime. Proportional regime means that the scaling of the number of rows is the same as the scaling of the number of columns. So ratio of rows to columns is some parameter alpha. It will play an important role soon. And the set of solutions, this is just a notation. Let sigma set be the set of sigma, little sigmas, vectors that satisfy, that are the solutions. Now, this set is a random set because the matrix A itself is a random matrix. Furthermore, it might be empty. It might not be empty, and that's a random event. So we can ask, what is the probability that this set is not empty? What is the likelihood that the solution does exist? That's a question number one. And the second question, and that's the question that we will investigate primarily in this talk, is can we provide it that somehow we can probabilistically guarantee that solution is not empty with high probability, for example, can we actually find it by fast aka polynomial time algorithm? And so that's the model, and these are the questions. Are there any questions from the audience about this? Should I clarify any of this? Let me know. Meanwhile, I will turn to the next page and tell you what we as a community know about this question. So regarding the first question, when is it the case that the solution set is non-empty, that at least one solution exists? This was resolved relatively recently in these two parallel papers that appeared in parallel. It turns out that existence or non-existence is a kind of a 0-1 law. Provided the ratio of rows to columns, alpha, is less than this number on the right-hand side, the solutions do exist with high probability, with probability approaching 1 as n goes to infinity. And when alpha is bigger than this threshold, the solutions do not exist with high probability as n goes to infinity. The number is just what it is. It's log 2 divided by negative log. Probability that the standard normal in absolute value is at most kappa. And kappa is that parameter of tolerance that is a part of the model. Okay. This number might look a little strange, but there is actually very simple intuition where this number is coming from. Let me share it with you. It turns out, and it's a simple kind of exercise, it's rather straightforward to compute the probability that any fixed vector sigma is a solution. So we fix sigma, and the reason is as follows. If you fix sigma without looking at the matrix, uncorrelated with the matrix A, and hit it with matrix A, and look at the vector, that vector has entries which are IID standard normal. And this is because the matrix has IID normals with variance 1 over n. This is why we needed variance 1 over n. That makes this vector entries standard normal. What is the probability that independent entries of standard normals lies in the interval from minus kappa to kappa, or all n of them? Well, that is just the probability that standard normal is in this interval to the power, which is the number of entries, and the number of entries is alpha times n. That's the number of rows. Okay. Well, okay. So that's the likelihood that there's a fixed solution is actually fixed vector is actually a solution. But we have 2 to the n potential solutions because because the space of potential solutions is a binary cube, 2 to the n points. So expected number of solutions we can compute, and it's given as 2 to the n times this probability. Well, if alpha is larger than this number that is stated in this theorem, this expectation goes to 0. And if the expected number of integer valued quantity goes to 0, that means that this integer valued quantity is 0 with high probability just by straightforward Markov inequality. Okay, so that gives you pretty much the proof why alpha has to be smaller than this number for the solutions to exist with high probability. The fact that solutions do exist with high probability when alpha is smaller than this number, that's more subtle, and that's where this work, that's the essence of these 2 papers. Okay, all right, I will pause to see if you have any questions on this. This is, so bottom line is that the existence of the solution is well understood. There's this threshold. If you're below this threshold, the solutions exist with high probability. If you're above this threshold, solutions do not exist with high probability. This is an existential result. Our focus now is on algorithms. When can we design an algorithm, fast algorithm, to find a solution if we are in a regime where the solutions do exist with high probability? Now, this becomes part of the large body of problems with random inputs where you want to find something algorithmically. In the worst case, this problem is NP-hard, but that's not of relevance here because the data is random. So the NP-hardness is a worst case statement. So for random instances, we might be hopeful to find the solutions all the time that alpha is smaller than this critical threshold for the existence. Well, something interesting actually happens to this model in when alpha is smaller than the critical number. And so this is where having a board would actually be helpful. So instead of a board, I'm going to be waving my hands a lot. I apologize for that. So as it turns out, for any alpha, for any number of ratio of rows to columns, the solution space is mostly clustered. So what does it mean? It means that all solutions are like needles in a haystack, separated by a linear in n distance. So they're really far from each other, and there's no neighborhoods of solution. There's one solution in here, and the other one solution is there, and another solution is there, and most of the distances are linear. Why is it interesting? Okay, it's just a fact from the solution space geometry, something curious. What's so relevant? What's so interesting about that? But the thing is that for all prior models, similar models that exhibit such a phenomena, that usually suggests that the algorithms do not exist. Okay, so based on that, one would conclude that, okay, there shouldn't be an algorithms that work for this model for any alpha strictly positive. And a case in point is the so-called random k-set model, and I'm not going to introduce it now. I'm going to just leave it for the offline if you're not familiar with that. So this is a random instance of the constraint satisfaction problem, the K-set, the well-known K-set model. It does exhibit this phenomena, clustering phenomena after some critical threshold alpha, and the algorithms do exist up to this alpha, and nobody was able to construct algorithms above the alpha, and there is good evidence that they do not exist other than the brute force. So we're talking about fast polynomial time algorithms. Okay, but the puzzling thing, and this is where the curiosity of this model comes into play, is that algorithms actually do exist for this model for some small enough alpha. And there's a couple of versions of it. The most relevant one is, and also the most recent one is the paper by Bansal and Spencer. It's somewhat related to the discrepancy work that they have Nikhil Bansal and Bansal Spencer have done. As an implication of this work, the algorithms do exist for some alpha positive. Smaller, of course, it's smaller than this critical threshold because that's where the solutions exist, but they do exist, and despite the fact that the solution space is clustered. And this was interesting, and it was subject to several papers, some by physicists, some by mathematicians, trying to make sense of it. How is that the case that clustering, which is nominally usually an abstraction to algorithms, does not preclude algorithms in this case? And that's what we want to demystify. Okay. Well, that suggests, at the very least, clearly clustering is not an abstraction to algorithms. Now, what is the abstraction to algorithms? In this work, we have engaged a different tool related to clustering, but it's different, and I will introduce it shortly. It's called overlap gap property. And this property is actually, unlike clustering, as a provable barrier to classes of algorithms. Not all polynomial time algorithms, because that would prove P not equal to NP, but some large enough class of algorithms, and I'll talk about that. So what is this property? Let me introduce this property formally, and then give you a little bit of an intuition. For simplicity, let's assume that kappa, this margin of error, is 1. Then you can work out a critical threshold, alpha, using this formula that I gave you earlier. Let me go back to this. So this is the formula. I'm trying to highlight it here. I hope you can see it. So you plug kappa equal to 1, you compute this number numerically, and that number turns out to be 1.82. So you know that if alpha is less than 1.82, solutions do exist with high probability. But something else, you know, for this model, let me go through this slow because it's a little technically dense, but the intuition should be simple. It turns out that there is a different threshold here, 1.71, a smaller threshold, such that whenever the ratio of rows to columns is in the interval from 1.71 to the largest for which the solutions exist, 1.82, there exist two numbers, nu1 and nu2, with the following properties. Every two satisfying solutions, every two vectors sigma and tau, which successfully solve this problem, have the property that their distance between them is either at most nu1 or at least nu2, cannot be in between. So the overlapping, the angle between them has to be either at most nu1 or nu2, and d denotes here a Hamming distance. Roughly speaking, this is just articulating the following idea. As you approach the critical threshold alpha, every two solutions are either quote-unquote close to each other or far from each other, but they cannot be in the in-between range. Okay, it's a property, so what? We can prove it, but it's a property, so what? Well, the key thing about this is that this type of property, the overlap gap property, is a provable barrier to classes of algorithms. And some classes of algorithms, I'll talk about that. And key question is that whether this class includes the earlier algorithm by Bansal and Spencer and Kim and Rush, in other words, algorithms which are successful. So presumably right. So this property is a provable barrier to some classes of algorithms, and there's several now surveys articulating this idea. So it is fairly compelling that the presence of this property is a true barrier to algorithms. Not all in polynomial time algorithms, but at least to large classes of algorithms. Conjecturally, actually, to the all polynomial time algorithms, but that would be harder to prove. Okay, so all right, to summarize, what do we have? At least for kappa equal to 1, close to the critical threshold, we have this property. It is a barrier to algorithms. On the other hand, if alpha is pretty close to 0, then there are these two papers that provided algorithms, so they do exist. Okay, so one question is that, is there maybe contradiction? Is there a coincidence? And sort of, and well, for starters, I would say it is easy to verify that the success of these algorithms for small enough alpha is for alpha much smaller than this critical threshold 1.71 that we have. But now we want to do a little more, right? So known algorithms work for alpha much smaller than 1.71. Presumably after 1.71, algorithms do not exist. So we want to understand where is the real threshold for the algorithm. Okay, are there any questions in the audience? I don't hear anything. I can't watch the chat, so I'll.
If you have questions, just raise your hand.
Yes. Okay, so
I actually have a question for you, but it's probably very easy to answer. Nu1 and Nu2 are constants, right?
yes.
Okay. Thank you.
Yeah, sure. And well, it's a good question. So the scaling is important. Scaling is important. For every alpha in between these two numbers, you can find U1 and U2 constants for which this is the case. Yeah. Was there another question?
We have another question. Yeah, please go ahead.
Wait, so the mu1 and mu2 are a function of the, I thought they exist independent of your choice of sigma tau, right?
So the question is, do mu1 and mu2 exist independently of sigma and tau?
No, I mean, it's reverse in a sense that nu1 and nu2 depend on alpha. So for each alpha, you can find constant u1 and u2 such that for every sigma and tau, that property holds. So you identify those two constants. So this is like maybe like a code distance between the solutions. So it says that every two solutions has to be angled at most mu1 or at least mu2. I don't know if this answers the question.
Yeah, I was just wanted to ask, like, do those have a closed form? Or?
Do they have a closed form?
Not quite, because you have to solve some nonlinear equations, set it equal to 0 and find the answers, but it's numerically easy to find.
Thank you. We can
okay, so, okay, right, but feel free to continue with questions. Meanwhile, I'll continue. So what is our next goal in this talk in general? We want to actually identify a right threshold, right? So this is still, there is still a mismatch between the threshold 1.71 and the success of algorithms, but we want oops, sorry, okay, something happened to my second Zoom. Okay, good, I'm back. So we want to get matching bounds in some sense. So for that, I have to torture you with some modification of the overlap gap property. It's not really that important to understand the details of those if you have just a feeling that's good enough, but I have to go through that anyway. So first is an extension of this property is to ensemble version. So it goes as follows. I'll give you a sort of detailed version, but then give you a sort of high level idea. Detailed version is that suppose you have not one, but two independent copies of the matrix A. So you have matrix A and independent copy A tilde. And then you create a flow from A to A tilde, which is A of t. This is the standard Gaussian flow from one Gaussian matrix to another Gaussian matrix, shows up in many of the Gaussian analysis. It's easy to see that every A of t is Gaussian, so it's a legit instance to our problem. Still IIDs, still normal entries. As it turns out, this property that I have described holds not only for the single instance A, but it holds across the entire flow. So what it means that for the same parameters, nu1 and nu2, for every times s and time t in between 0 and 1, and for every solutions in the instance indexed by s, and any other solutions indexed by time t, the same property holds. Their distance is at most nu1 or at least nu2. Okay, so this is kind of a geometry description of the whole flow of the instances as opposed to one. That turns out to be important for the algorithmic discussion in a way that I'll try to describe next. And final, and this is the most torturous version of the overlap gap property that I will discuss with you, is the multi-overlap version. Ensemble, there is a flow version, but multi-overlap. So what does the multi in reference to? The overlap gap property I have just introduced is in reference to pairs of solutions. So two solutions, distance small, distance large, that's the deal. It turns out that it's important to consider geometry not just of pairs of solutions, but m-tuples of solutions or k-tuples of solutions, right? And it goes as follows. So now we create not just my apologies. This I have doubled down on parameter m. This m is different from the number of rows. My big apologies to that. I need to fix it. So we create some k copies of the matrix independently, and now we create a flow from a single copy to k different copies. So now it becomes like a tree, or sometimes if you draw it, actually looks like a Jewish menorah, so to speak. It's not very helpful connection, but maybe you can visualize it. It's like single stem, and then kind of flows to different copies. Okay. Well, this is a dense slide. I'm not going to go over that in detail, but the point being is that some version of the overlap not allowance, sort of not allowing in distances between in some interval, holds for this multi-version, provided this number of k-tuple k is large enough. And the key thing here is the onset of this number. That happens in this that happens after this threshold, kappa squared log 1 over kappa. Admittedly, that happens provided kappa goes to 0. So this is asymptotic statement, but it will be helpful for us. So here we have this new threshold, kappa squared log 1 over kappa. It has the property, and arguably perhaps not interesting yet, has the property that once alpha is larger than this threshold, some bizarre overlap gap property happens for the m-tuples or k-tuples of solutions. Why is it important? Once again, because even this k-tuples of solutions, this multi-OGP, is still a barrier to algorithms, right? Okay, now the question is, how good is this threshold with respect to the known algorithms, right? We have the known algorithms. I mentioned 2 of them. So yeah, this is just an informal statement of the same thing. So I'm going to skip this slide. Well, here's where now something interesting happens. The best of these 2 algorithms, what happens to be Bansal and Spencer, this algorithm works, and you can work out up to what threshold of alpha it works. It works up to pretty much the threshold I've just shared with you. It works up to the threshold kappa squared. And this threshold is slightly larger, kappa squared log 1 over kappa. The satisfiability threshold is way larger. It's more like a 1 over log over 1 over kappa. Okay, so what do we have here? We have found a suspect. We found this suspected threshold, this multi ensembler or GP, that might be a right barrier to algorithms. So we have the suspect, we can sort of put him to jail, but only for a certain time, until we prove the guilt beyond a reasonable doubt. But now it's just a person of interest, so to speak. Okay, and I'll explain why is it a person of interest. And the reason is that this threshold is just at this stage is just partially coincidental, in the sense that yes, above this threshold some geometry changes, some geometry thing happens, fine, and below this threshold there exists an algorithm. But those things could just coexist completely separate. Maybe the algorithms are successful up to here because nobody was clever enough to go beyond that. On the other hand, maybe this threshold is not a barrier to algorithms of the kind that Bansal and Spencer satisfy, right? So we need to match the class of algorithms that this is a barrier of to the class of algorithms that includes Bansal and Spencer algorithms, so that we have a more compelling picture. I know I'm loading a lot on you, but this is the key idea. We need to link the property of the algorithms and the property of the algorithm ruled out by this threshold, and property of the algorithm's success that is of which Bansal and Spencer is a special case. So now I need to tell you a little bit what can specifically be ruled out by the overlap gap property, right? I said it's classes of algorithms. It's not all the algorithms, not all polynomial time algorithms. What can we rule out of this? Up until this work, the classes of algorithms that we were managed successfully to rule out is the class that we call, that's fairly kind of a boring term for it, is the class of the stable algorithms. So what is a stable algorithm? This is a class of algorithms which are largely insensitive to small changes in the input data. And you can apply it in this context, you can apply in general context. So in general, algorithms work on input. You give it to the algorithm some input and that produces some solution. So we call it stable if changing this input slightly by one bit or maybe one entry, graph entry or matrix entry, it's not going to rearrange your solutions drastically. It's still going to be mostly the same solution, maybe with just a few modifications here and there. This is, of course, an informal description. Well, with the right quantifiers, epsilons and deltas, you can make it precise. But the point is, well, 2 points. So before I get to the theorem, point is that OGP is a barrier to stable algorithms, right? So if we are actually prove or verify that the algorithms that we have discussed today, there's two of them, Kim and Rush and Bansal and Spencer, if they are stable, then we have a complete theory, right? So we have a theory that stable algorithms succeed up to a certain threshold, and above this threshold, stable algorithms fail because of this fact. Okay, so then a key question is that are these algorithms indeed stable so that we can create a complete theory? Well, the answer is partial. It's mixed. I wish we were hoping for the answer to be as clean as that. Both algorithms are stable, therefore they work only up to the OGP threshold, and after OGP threshold, no stable algorithms can exist. Kim and Rush algorithm, the first one they've introduced, is stable. With the right parameterization, with the right quantifiers, you can make it. I gave it some little bit of kind of semi-precise attempt. It says that the level of perturbation T in this flow, how much you need to tolerate, how much change in the matrix you can tolerate so that the output does not change too much. So the distance between the algorithms produced by after time T flow is sublinear in N, and therefore the two solutions, remember this is N3 solutions, if the distance between is sublinear, then these are binary solutions, then mostly they are agreed, right? Okay, good. So Kim and Rush is stable, but what about Bansal and Spencer? This is the strongest algorithm of this is the strongest algorithm of the two. Okay, is that stable? We spent quite a bit of time trying to prove that it's stable, and instead we came up with a fairly plausible argument that in fact it's not stable. The algorithm Bansal, I apologize for that, Bansal and Spencer is not stable in the sense that if you change the entry of the matrix a little bit, that might have a chain of implications so that your final solution looks entirely different from the one that you had. So we were pretty despondent at the stage, so thinking that, okay, then we don't have a complete theory. Is there a way around that? And then a new idea came, which was just to look at the same problem from a different angle. What properties the Bansal and Spencer algorithm has? What type of property that has? Maybe it has a different property that is also ruled out by this multi-overlap gap property. Well, okay, as it turns out, the Bansal and Spencer does have a feature, an important feature of the algorithmic feature. It is an online algorithm. It's an online algorithm. What does it mean? Again, I'm going to rely on fingers here. So online means that, okay, so we need to find a solution that is a vector of plus minus ones. So we need to find this plus minus ones. The way Bansal and Spencer works is as follows. For the first entry, for the very first entry, that's dependent only on the first column of your matrix. It's just a fact. The second entry depends on the first and second column of your matrix. The third entry depends on first and second, third column, and so on. Every entry, kth entry of the algorithm depends on all k previous columns. In that sense, it's online. You kind of scan your matrix from the left to right, column by column, and then you set your solutions that way. Okay, it's an online algorithm in that sense. It's a feature. So what? Right, so that's just saying what I already said. It has an online feature. Well, the work around that was to realize that, in fact, online algorithms are also barriered, abstracted by the multi-overlap gap property. And that's a theorem. Every online algorithm, in this sense roughly that I've described, can be implemented on interpolated instances to create m-tuples of solutions or k-tuple solutions, which we know do not exist by this property, and therefore it has to fail, right? So overlap gap property is a barrier of the new kind of algorithms online, and now we have a complete theory, and that can be summarized as follows. There is this threshold, kappa squared log 1 over kappa. Until this threshold, class online algorithms succeed, in particular Bansal and Spencer algorithm succeeds. Above this threshold, every online type algorithm has to fail because of the overlap gap property, and arguably this is beyond kind of more compelling evidence to put this poor dude in jail. And I think this is all I wanted to share with you. I have some 5 minutes to spare for questions if you have any, but meanwhile, thank you for your attention.
Let's thank David. Do you have any questions? Yes, please. So the question is whether something else can be said for kappa not going to zero.
Good. Probably. Technically, it turned out to be very difficult. We don't know. We cannot solve this threshold. This threshold for the multi-OGP is something, and something exists for every kappa. We just cannot identify it in any kind of a succinct form, because it's just working with it's working with matrices of Gaussians, and just for technical reasons, we don't have any answers. That would be really good. For example, when kappa is equal to 1, what is the right algorithmic threshold for kappa is equal to 1? That's an open question.
Anyone else? So I actually have a question. So the OGP is a barrier to online algorithms, but this does not say that in principle there could not be something that's not online that could work above kappa square log of 1 over kappa?
Absolutely, absolutely. So this kind of sort of points to the kind of a general theme of this line of work, which is sort of what type of algorithms we consider kind of respectful to be ruled out. So why online, why stable, and so on. I mean, ideally, we would like to rule out all polynomial time algorithms.
Right.
If we managed, we would prove P not equal to in P, even stronger version, because we would prove P not equal to in P for average case instances. So that's too much to hope. So the guiding principle is that to rule out classes of algorithms which succeed below a certain threshold. So if you know that your algorithm that works up to a certain threshold has a certain feature, and you rule out that this feature is broken has to be broken above some threshold, then this at least gives us some partial satisfaction. One recent but not mentioned here big class of algorithms, very important class of algorithms that shows up in this line of work, but also in statistics, is approximate message passing, which is highly successful algorithms for many problems of this and similar kind. It has a certain stability property that can be ruled out then by the OGP. So once you know that you have an OGP, you know at least that approximate message passing and similar kind of algorithms have to fail. But I wish but this is a good question. This is a bit of an ad hoc exercise. It's what classes of algorithms are reasonable to be ruled out by this property? So, good question.
And I have one more question, which is there any interest in exploring what happens if you have non-Gaussian entries?
For this problem, it's not so much, because most of this thing goes through rather directly. There's a little bit of annoying thing with working with the flows, because once you look at the flow, it's no longer Gaussian. So, but if you have something like a Rademacher entries, then you create just a discrete resampling type flow. This kind of you resample entries one thing. Yeah.
I'm asking because sometimes, so I've seen this flow be employed from non-Gaussian matrices toward Gaussian matrices, right? So like in the universality proofs for random matrix theory.
Yes.
So it's possible that, you know, maybe someone could find something in that direction that would work. But thinking from an interest perspective.
No, I agree. It so happens that for this problem and these properties, they're fairly stable to changing of the distribution. So if you change the distribution to any reasonable zero mean variance one, or
to go through, right?
it would
What
go
about
through.
sparse? What about sparse?
That's sparse. We don't know much. That's a good question. And it's actually relates to some other conjectures such as Beck-Fiala and other things. So it's largely unexplored area. So I think the universality that you're alluding to will work if it is sparse but not too sparse. So if it's something like you have a super constant many entries per rows and columns, then probably most of this theory will go through. But that's to be checked.
That's very interesting. Any other questions? Thank you very much, and especially because you took time and you're sick. And thank you for a wonderful talk. Thank you.
Thank you very much. Good to see you.
Bye, David.
Bye-bye.
Sorry?